And so I think that the issue we were facing and that sort of motivated this paper was that there's no long-running discussion about how to connect MPI with the various +X asynchronous communication MPIs. That is, if we have the massive parallelism that Ryan was talking about, if we have GPUs, if we have lots of threads, if we have, pick whatever's coming down the pipe next, and we have MPI, which is in many fundamental ways very host-centric, how do we tie MPI to these asynchronous computations that happen on accelerators or other threads or things like this? And traditionally, and this is something that Ryan was getting at with partitioning, this is done by something like what's called a triggering interface. So you do some extensive setup or synchronization on the host MPI, you have some queue or atomic update or something that couples MPI to the +X side. And so you're trying to separate concerns, right? So the expensive things like matching, like setting up queue pairs, channels, these kinds of things are done once or periodically, and the cheap things, triggering communication, are done through a much simpler interface. And this limiting the complexity of the interface between MPI and the +X side is really a key element of this. So as you saw in partitioning, MPI ready, as Ryan said, could be reduced to something like a cache flush, an atomic increment, a flag update, depending upon your hardware, something very simple, something much less complicated. But all the semantics would go with an MPI sender and MPI receiver. And there's a lot of complicating issues here. So there's not just one +X environment. As we saw when we started looking at things, there's sort of CUDA and HIP kinds of things you see, but we also started looking at what people have been doing with SYCL, right? And there's a lot of different ways, a lot of different semantics, a lot of different programming systems that come with OpenMP versus NVSHM versus CUDA versus, pick your favorite thing. And the MPI specification has a lot of ambiguity and complicated historical decisions around things like persistence that in some cases complicate what, or wildcard, as Ryan mentioned, that complicate what otherwise might be relatively straightforward. And so as we kept talking to people and saying, okay, we need to start doing something to provide people APIs here, our first question was, where are we now? And so that's what motivated this paper, which is really trying to understand what the state of play is for all the various things that people have proposed up until we wrote this paper, because there's additional proposals as you see, for dealing with MPI+X triggering. So we spent a lot of time just digging through presentations, proposals, all papers, conferences, discussions, reaching out to colleagues, seeing what people were talking about. And we identified 9 different MPI+X proposals for doing triggering of MPI communications asynchronously. And those included both formal presentations, conference papers, presentations in MPI working groups, and informal ones. So, discussions in online forums and things like this. Some proposals included multiple distinct triggering APIs that we studied as separate proposals. So, for example, there's one on MPI+X, MPI ACX, which has both a stream triggering portion, and a kernel triggering portion based on partition communication. Some proposals around the same interface we aggregated into a single proposal. So with partitioning, there's been work on the traditional partitioning that Ryan talked about that's in MPI4. There have been proposals for MPI bus prepare. There have been partition collective proposals. We tried to sort of collect those to say, here are, at least as of when our paper was written, the 9 proposals we could identify for what people think we should do for MPI+X. So we want to understand what those things were, how to implement simple communication patterns in each of them, and then from there start trying to identify similarities and differences that are recurring issues. And so that's what our paper fundamentally did, was come up with a taxonomy and a classification scheme for current MPI+X triggering proposals. So that as we come up with a new triggering proposal, if somebody else comes up with a new triggering proposal, Joseph, I'd love to have a conversation with you, we can say, okay, look, how does this new proposal fit in to the taxonomy we have? Is the taxonomy sufficient? You know, how does it compare to what other people have done? And to that end, we also classify these nine proposals we identified into these various categories. One note, we didn't focus on non-MPI triggered communication interfaces. We didn't look at, to pick the obvious element, in-beach memory network, right? Which do GPU triggered communication, because it wasn't an MPI interface. So you can see that the implementations and specifications that came up on the right, those range from some work from the late 2010s in MPI+X called MPI+GPS, to a variety of proposals, some of which have implementations, some of which don't, up to an Intel GPU-initiated interface from Intel MPI that Dan Holmes was helpful enough to give us, was very helpful to provide us more information on. And so let's go through some simple examples so that people understand what we mean by triggering. Right? So in this case, this is the MPI+X stream specification and implementation in the current version of Image. So if you go look at Image today, this interface is in Image. You can download it, you can install Image on the system with GPUs, you can run it. And it works. And so the basic idea here is that it defines this MPI+X stream, which you associate with a communicator by creating a new stream communicator. And then once you've done that, you can enqueue sends and receives with new MPI operations, MPI+X send enqueue, and receive enqueue to that stream. And then you can synchronize on the underlying CUDA stream to await those MPI operations to happen. Right? So there's a lot of new calls going on here. So in the MPI+X version, there is a new stream type, which you can associate CUDA streams with through this MPI info. There's a new stream communicator that you need to create. And then there are new sends and receives for the operations you want to queue. MPI includes not just send and receive, but also all reduce now. And so there's a lot of, in this case, new call abstractions, as opposed to trying to reuse existing MPI operations. And there's new semantics here. So the MPI streams that the MPI team proposed propose specific changes and clarifications to the MPI concurrency model. And those of you that have sometimes hung around the MPI hybrid working group will know this is a long-standing issue of discussion in the hybrid working group about exactly what the semantics of MPI are or should be around concurrency. The MPI proposal takes a clear position as to what that should be and how this proposal relates to that. One thing to note is this, getting to something that Ryan again mentioned previously, requires MPI matching in the data path. So as I said before, some MPI triggering optimizations try to move expensive things out of the triggering path. But here we're enqueuing what is basically a standard point-to-point send and receive. You'll note that there are tags, right? So there's a tag in this call, and so those tags are putting things like matching in the data path with the simplicity that goes with that in terms of the API for the programmer, the application programmer, with the complexity that goes into that with the, in terms of performance with the MPI implementer. So this is the one end of the spectrum, stream triggering. And so we're putting operations onto streams, and the idea is that when my kernel finishes, then the sends and receives that are after that in my CUDA stream also get run automatically. Right? MPI+X send in queue and receive in queue, return immediately. Right? So their return, just like an ISEND, doesn't mean that you can actually look at reuse the buffer. In this case, you have to do a CUDA stream synchronize to know those operations have been done, so to know that the buffer is actually usable. This is a two-sided stream trigger version. Ryan talked about, what Ryan talked about was what's typically referred to as kernel trigger. That is here,
the GPU scheduler is causing sends and receives to be triggered and happening. In partitioning, operations inside GPU kernels, like calling pready inside a kernel, are triggering communication operations. Right? So these are both two-sided. Let's contrast that with another proposal that it's on archive, which is one-sided. And so this is a proposal from HPE that uses RDMA, the post-start complete wait part of RDMA, the MPI RMA that many people tend to not think about or not remember. But they use it in a very interesting way to do string triggering. So in this case, MPI a window is created, an MPI window already exists. When start is when start. Put is put. So when start and put, start the appropriate epochs and say, here are the operations I want to do during this epoch. Right? So for example, I'm going to do puts for my sends after I start my window. And then when I call complete, that's when the put might actually happen. Right? Likewise, when I'm going to receive data, I start my exposure epoch. I put my post on the stream and then put my wait on that post on the stream as well. So this is a little different. Right? In particular, we're mixing old and new MPI instructions. And so we're reusing MPI when start, MPI put, right? But we're adding complete stream, post stream, and wait stream to add to change the semantics of how MPI communicates. Right? And so one thing that's interesting here is the RMA semantics are a little different. That is, traditionally in one-sided, between calling MPI put and complete, MPI has the option of when to move data. Whereas in this implementation from HPE, the put, because it's not stream triggered, right? This put is just a put, is basically only supposed to happen when complete is called. So this is the kind of thing that some string trigger proposals do too, which is they may make subtle changes in MPI semantics, in this case not worse, but in this case strengthen semantics. Finally, there's no need for complex matching or agreement. This is RMA. So we're just doing puts and gets here. So in this case, the when start and the put are when we start declaring the expensive things that we're going to want to do. The complete stream, post stream, and wait stream are the ones that do the lightweight things to actually make things happen, like ringing doorbells. And there are lots of other interesting variants that we looked at and saw when we looked through these things. The in-package code I talked about changed the semantics of MPI send. So that MPI send returned immediately, but you couldn't reuse the buffer. We've already talked about partition communications, kernel triggering. Intel's signal-oriented kernel triggering was quite interesting, and it's sort of RMA-ish as well. And there are others. So I encourage you to read the paper to see all the various things. We found there's been a lot of different things done here, and part of what we did was just surface what all has been done so we could start seeing where we start converging as a community. And so we identified basically 4 areas and something like 12 different categories in 4 areas that these various proposals were similar or different on. So that's, what GPU control path is it using? How is the API designed? So key features we saw in API design. How does the proposal handle ordering and concurrency? And what are particular features of the implementation that are worth understanding? And so most of these were relatively self-explanatory. Things like, does this proposal change MPI semantics, and if it does it strengthen it like we saw in the HPE one-sided case, or does it weaken it like we saw in the MPI GBS case? Does the GPU, is there an operation to support, to handle
completion, how do we do product communications, kinds of things. I think it's easier to explain some of these categories with a few implementations. So that's what I want to focus on. So just some highlights here. So some of these proposals reused existing MPI APIs or abstractions. Right? And that's what we saw in the previous examples I just showed. So HPE one-sided reused at least portions of existing MPI APIs, whereas HPE has a two-sided API, it's in the paper, that is completely new. Right? It doesn't reuse any of the existing MPI abstractions outside the communicator, it just says, have at it. Do operations separate the initialization and starting phases of MPI operations? So MPICH and MPI GPS and Intel operations don't separate initialization and starting. Right? So if you look here at MPICH, like send and queue does both initialization of an MPI send and start send. Whereas if you look at HPE one-sided, when start is in some sense initializing an MPI operation, as is MPI put, whereas MPI-X when complete stream is actually starting the transfer. Now, I'm sort of abusing initializing and starting in the RMA context because those are mostly two-sided concepts in MPI standard, but the issue is I think still relevant here. And most of the stream-triggered APIs rely on the +X side of things to handle waiting on stream-triggered requests. That is, if I do something like enqueue an MPI send with MPICH, and then call MPI wait or MPI wait off, it's often not clear from the specifications or papers if that's legal or what happens in that case, right? So three areas that I want to highlight is there some abstraction for sequencing MPI operations? So MPICH and MPI Extreme and HP's two-sided make a new MPI abstraction, something like a stream, that sequences what happens on MPI in terms of the ordering of MPI operations. Whereas most other APIs left that undefined, or said that was basically provided only by the existing semantics of MPI, which we like to argue about. Only the MPICH proposal was very careful and thorough on exactly what the concurrency specifications were, what it did in terms of concurrency with other MPI operations. So if you want to think about what this looks like, if I enqueue two MPI sends to a stream on a communicator, right? They may not have been started yet. They've been initialized, maybe. They may not have been started. And now I call another send or receive on that communicator. What exactly are the semantics of that? How does MPI operations which are enqueued on a stream then initialize the MPI sends and so their matching order is set or not? That's not always clear. And finally, there's some real implementation considerations around progress, and that is, can the GPU and the NIC completely progress operations without host intervention? So as examples, partitioning, like Brian showed, is meant to be able to do this. The HPE one-sided example I showed can do that. Most other examples did not have and it was not clear how you would make an implementation that was purely GPU and NIC progress without involving host. And so, we looked at this a lot and had some takeaways that I'd like to at least briefly talk about. One, persistent, and in many cases, these are gaps in MPI. And it's one that Ryan hinted at when he talked about persistence in partition communication, is that the persistent operation semantics cause proposals to re-specify existing MPI operations. So there's a lot of cases where we saw, more than one case where we saw something like an MPI-X in queue send or send in queue. That's because you couldn't usefully say, declare, there was no reason to say declare an MPI persistent send and enqueue that separately, because the persistent send isn't matched. Or what you'd like to have is that send, if it's persistent, know where its data is going to go when you enqueue it so you can do one-sided data movement. The semantics of traditional two-sided persistence don't fit that, which is part of why traditional communication changed though. You need a consistent way to cause research and remote partners are ready for communication so you can do one-sided data movement in progress. HP resorted to using one-sided to do that. Most all APIs lack a clear, well-defined concurrency model. There is limited support for GPU-triggered collectives. MPI had it, the HPE had it, HPE one-sided has some Weaver collectives. And then how you check for completion, of true commercial operations is really highly dependent on features of the programming environment. In most cases, the MPI proposals did not provide MPI operations to let you know whether your communication operation is done. You had to resort to something outside of MPI to know if your MPI communication operations were done, which is something very different from how most MPI programmers are used to thinking about things. Not necessarily bad, but just very different. A few extra thoughts while I'm here. Different people mean different things by GPU triggering. So when I say GPU triggering, in some cases I'm vague about it. Sometimes people are talking about the API feature. And that is, if I say GPU triggering, I mean I can put the MPI operation on a GPU stream programmatically, right, and have it work like just other things that work asynchronously. For other people mean GPU triggering as in the GPU directly triggers the NIC to cause a send to happen. We don't really have example abstractions and benchmarks here. The detailed semantics of a lot of these APIs really matter a lot and not well defined. And one of the big challenges here is that all these APIs have to take into account the shared capabilities of current network interfaces and programming environments and the future interface, the future characteristics of these network interfaces, which vendors in many cases not quick to tell us. So future steps, next steps in future work, I think really where we need to be going and what we're in the process of doing is collecting and curating documentation and source code on stream-triggered APIs, prototypes, and supporting fabric interfaces. We've been doing work on stream-triggered just like Ryan has in terms of coming up with implementations. It is remarkably difficult to get good implementation details about what some of these fabrics can do and what some of the GPUs can and can't do semantically in terms of memory barriers and things. You can go up to your elbows in NVIDIA code and sometimes find nuggets of documentation, but this is difficult. And so just having consistent documentation would help a lot. Another thing that we don't really have are good applications and frameworks, things like, Halo exchange abstractions, COCOS or Raja or OpenMPI communication abstractions that people want to use to drive the MPI level APIs. To some degree, we're programming and specifying APIs to the ether and hoping somebody likes what we propose, as opposed to saying, here's what applications need for string triggering, so here's what we should do. But where we need to end up going is just doing the hard work of proposing alternatives, debating what we should be doing, arguing with each other, which we in the MPI can really don't like arguing with each other at all, and converge on string-triggered APIs that leverage the lessons learned from existing proposals. I'm about out of time, and as I said, I encourage you to take a look at the paper and start engaging in work of helping figure out what the next what proposals should look like. I'm looking forward to Joe's paper to see what he's proposing. If I were to design a true API, sitting here, and Ryan was heading the circuit, I think one side is in pretty good shape, and I think kernel triggering is in pretty good shape. I would focus on a two-sided string triggering API that still allows for one-sided data movement. I think queuing starts and waits from what we found looking at what MPI+X does, what MPI did, what HPE two-sided is a pretty natural API. It's what the community knows that a lot of programmers like. We should specify operations based on existing capabilities, things like persistence whenever possible. And if persistence is broken, you should figure out how to fix it. Leveraging existing ideas to try to one-side movement like prepare is a good idea. One I think is really important, I mentioned in Ryan's talk, is thinking about collectives is really important. Stream sync is important, but there's a chunk of hardware systems where even if you're doing GPU signaling up the NIC, you still need to do memory barriers or cache work that is that's per trigger. And so if you can aggregate more communication per synchronization between the GPU and the NIC, you can make some pretty substantial savings. And we're looking at some things in this direction. I'm not going to go too far there. I'd like to take some time to acknowledge my collaborators. I have a lot of collaborators that we work with in this. In addition to my co-authors, Amanda Benz at UNM, Matthew Desange, Carl Pearson at Sandia, Ryan Gray at Queen's University, have all been really helpful to discussing these ideas, helping guide our thinking and provide insight into these over the years. I'd like to thank a variety of the authors and designers and intenders of the string trivial proposals, Dan Holtzman-Tell, Uju from Argonne, Jim Dines at NVIDIA, Larry Kaplan at HP, who provided some very helpful insights into what they were thinking, where they were going, what the status of the implementations are. MPI hybrid working group members were also very helpful here. I'd also like to take the time to thank some of the anonymous paper readers. We had a number of very thorough, very thoughtful reviews from our paper that really helped us refine our thinking and fix some things in the paper. The paper wouldn't be where it is today without the help of the paper reviewers. And finally, I'd like to thank the U.S. Department of Energy for our funding and support of this research. And with that, I'll be happy to take some questions.
Okay, so thank you very much for proposals. So questions?
Thanks for the talk. When I saw the example with the MPI streams, I just wondered, like, how's the interoperability with, let's say, if you use MPI plus CUDA and then you have CUDA streams, is there any like design for them using these streams within your stream PQ?
So in the in-pitch example, right, which is the one I showed, that's explicitly meant, I can go back to it, that's here. You're explicitly associating the CUDA string, right here on the left, or MPI+X info set X, the CUDA string with the MPI string. So if the MPI operations enqueued on that MPI string are sequenced with kernels enqueued to that GPU string. So you can enqueue a kernel, then enqueue a send, then enqueue a kernel, then enqueue a receive. And that send will be initiated and started after the first kernel, in GPU stream order. So that's the idea behind these string trigger proposals, is the ability to put MPI operations onto GPU strings. And to do that, you have to have some way of associating a CUDA string with an MPI operation, like an MPI communicator or an MPI or something else. Right? And how to do that is really where we're all debating and discussing what to do.
Thank you.
Okay. There will be time for one more question.
Thanks for the talk. I'm happy to announce that I'm going to add one more to this.
That's right.
So if I understand one of your last slides correctly, you would advocate for a more explicit extension to MPI that makes it explicit that operations are enqueued into the stream. Because we're doing the opposite in what I'm going to present. I'm just curious about what your position is.
My current thinking, right, and this is, again, we're discussing this, is that something like a persistent send
is a nice, and it's a combination of a persistent spend and a string to say, enqueue this persistent operation on, into some set of sequence operations is a relatively easy way to think about things. That's pretty natural for programmers who are used to thinking about enqueuing kernels. They enqueue communication on the strings. Enqueuing communication on the strings seems like a pretty natural way to do things. If I look at what a lot of programmers do for programming GPU code, that's what they're doing, they're enqueuing compute on the strings, and then doing a string sync, and then doing synchronous communication, and then enqueuing more things on the strings. And I think that's a relatively, I think that's a pretty natural way to do things. That's one of the reasons I try to think about what it would look like to program this inside an application. But it's by no means the only way to do things. And I'm ready to seeing what other alternatives are out there.
My problem with persistent, it doesn't work for the use cases that we have. So I need something non-persistent.
So,
Okay.
I'm curious what those use cases are. But I think I'm running out of time. We can take that offline.
Yeah.
Be happy to discuss that some more.
We should probably discuss it.
So let's have the next talk, and then you can maybe have a better view. Thanks a lot. So,